Have you ever looked up at the sky and wondered about the bright star that shines during the day? That bright star is actually a giant ball of hot gas called the Sun. It's the closest star to our planet, Earth. The Sun is incredibly important to us because it gives us light and warmth. Without the Sun, there would be no life on Earth. The Sun is so big that you could fit over 1 million Earths inside it. It's also incredibly hot, with a surface temperature of around 5,500 degrees Celsius. That's hot enough to melt anything we know of on Earth. Even though it's so far away, the Sun's light and heat reach us here on Earth. This is why we have day and night, and why we experience different seasons throughout the year. The Sun is an amazing object, and in this essay we'll learn all about it. Billions of years ago, the Sun wasn't a star yet. It was just a part of a vast, cold and dark expanse of space. It was just a giant cloud of gas and dust floating in space, known as a nebula. These nebulae are often the birthplaces of stars. Over a very long time, gravity started to pull this gas and dust together. This process is slow and takes millions of years. Gravity is a force that pulls things towards each other. It's the same force that keeps us grounded on Earth and governs the motion of planets and stars. As more and more gas and dust clumped together, the cloud started to spin faster and faster. This spinning motion caused the cloud to flatten into a disc shape. The center of the cloud became very hot and dense. The temperature and pressure in the core increased dramatically. Eventually, the pressure and heat at the center became so intense that nuclear fusion began. This is the process that powers stars. Nuclear fusion is a process where atoms, the tiny building blocks of matter, combine to create new elements and release enormous amounts of energy. This energy is what makes stars shine so brightly. This energy is what makes the Sun shine and produce heat. Without this energy, life on Earth would not be possible. The Sun is mostly made up of hydrogen, the simplest and most abundant element in the universe. Hydrogen atoms fuse together to form helium, releasing energy in the process. The Sun continues to burn hydrogen in its core, producing the light and heat that sustain life on Earth. This process is known as the proton-proton chain reaction. It's been doing this for about 4.6 billion years, and scientists believe it will continue for another 5 billion years or so. During this time, the Sun will go through various stages of its life cycle, eventually becoming a red giant and then a white dwarf. The Sun is not only the center of our solar system in terms of its location, but it also plays a crucial role in keeping everything together. Just like the Earth's gravity keeps us on the ground, the Sun's gravity is what holds all the planets in our solar system in their orbits. Imagine swinging a ball on a string around your head. The string represents the Sun's gravity and the ball represents a planet. The Sun's gravity pulls on the planets, just like the string pulls on the ball, keeping them from flying off into space. The strength of the Sun's gravity depends on the mass of an object and its distance from the Sun. The more massive an object is, the stronger its gravitational pull. The closer an object is to the Sun, the stronger the gravitational force it experiences. This is why the inner planets, like Mercury and Venus, orbit the Sun much faster than the outer planets, like Jupiter and Saturn. They experience a stronger gravitational pull because they are closer to the Sun. Life-giving energy. The Sun's importance to Earth. The Sun is essential for life on Earth. The light and heat it provides make our planet habitable. Plants, the primary producers of energy in most ecosystems, rely on sunlight for photosynthesis. Photosynthesis is the process by which plants convert light energy from the Sun into chemical energy in the form of sugars. These sugars are the building blocks of plant tissues and provide energy for animals that eat them. The Sun's energy also drives the Earth's climate and weather patterns. The uneven heating of the Earth's surface by the Sun creates differences in air pressure, which in turn cause winds. The Sun's energy also powers the water cycle, which is essential for all living things. The Sun's warmth evaporates water from oceans, lakes and rivers, which then condenses into clouds and falls back to Earth as precipitation, replenishing our water sources. Without the Sun's energy, Earth would be a cold, barren, and lifeless planet. Day and night, the Earth's rotation and the Sun. Have you ever wondered why we have day and night? It's a fascinating phenomenon that we often take for granted. It's because the Earth spins like a top while it orbits the Sun. This spinning motion is what gives us the cycle of day and night. This spinning is called rotation. The Earth rotates on its axis, an imaginary line that runs from the North Pole to the South Pole. It takes the Earth about 24 hours to make one complete rotation, which is why we have a 24-hour day. This period is what we call a solar day. As the Earth rotates, different parts of the planet face the Sun. This constant movement means that at any given time, half of the Earth is experiencing daylight while the other half is in darkness. The side of the Earth facing the Sun experiences daylight, while the side facing away from the Sun experiences night. This daily cycle is essential for life on Earth, influencing everything from our sleep patterns to the behavior of plants and animals. Imagine shining a flashlight on a ball in a darkened room. This simple experiment can help us understand how the Earth's rotation affects the distribution of sunlight. The side of the ball facing the flashlight is illuminated, while the other side is dark. This is similar to how the Sun illuminates one half of the Earth at a time. As you rotate the ball, different parts of it become illuminated, just like different parts of the Earth experience daylight as it rotates. This rotation is crucial for maintaining the balance of temperatures across the planet. The Earth's axis of rotation, the imaginary line around which it spins, is tilted at an angle of about 23.5 degrees. This tilt is not just a random feature, it has significant implications for our planet. This tilt is what causes different parts of the Earth to receive varying amounts of sunlight throughout the year, leading to the seasons. Without this tilt, we wouldn't experience the rich variety of climates and ecosystems that we do. The changing angle of sunlight affects everything from the length of days to the intensity of seasons, making our planet a dynamic and ever-changing place. Inside the Sun, a closer look at its structure. The Sun, our closest star, is a fascinating celestial body that has intrigued scientists and astronomers for centuries. Understanding its structure helps us comprehend not only the Sun itself, but also the broader workings of other stars in the universe. The Sun is a complex and dynamic object with several distinct layers, each playing a crucial role in its overall function. These layers work together in a delicate balance, producing the light and heat that sustain life on Earth. Let's take a closer look at the Sun's structure from the inside out, starting from the core and moving outward through its various layers. The core is the Sun's innermost layer where nuclear fusion takes place. This process involves hydrogen atoms fusing together to form helium, releasing an immense amount of energy in the form of light and heat. Temperatures here reach a staggering 15 million degrees Celsius, providing the energy that powers the Sun. This energy is crucial for the Sun's stability and longevity, ensuring it continues to shine for billions of years. Surrounding the core is the radiative zone, where energy generated in the core slowly makes its way outward in the form of radiation. This zone acts as a buffer, regulating the flow of energy from the core to the outer layers. This zone is so dense that it takes photons, the particles that make up light, hundreds of thousands of years to travel through it. The density of the radiative zone means that photons are constantly absorbed and re-emitted, making their journey incredibly slow. Above the radiative zone lies the convective zone, where energy is transported through convection. This layer is less dense, allowing for more dynamic movement of energy. Hot plasma rises from the radiative zone, cools as it reaches the surface, and then sinks back down, creating a churning effect. This convective motion is similar to the boiling of water in a pot and is responsible for the Sun's granulated appearance. The photosphere is the visible surface of the Sun, the layer we see from Earth. It is the source of the sunlight that reaches our planet, making it essential for life. It's relatively cool compared to the Sun's interior, with a temperature of around 5,500 degrees Celsius. Despite being cooler, it is still incredibly hot and emits the light that illuminates our days. Sunspots, cooler, darker regions on the photosphere, are caused by intense magnetic activity. These spots can be larger than Earth and are indicators of the Sun's magnetic field dynamics. Above the photosphere is the chromosphere, a thin layer of the Sun's atmosphere. This layer is less dense and more transparent, allowing us to see through it during certain conditions. It's visible during a solar eclipse as a reddish rim around the sun. The chromosphere's reddish color is due to the presence of hydrogen gas, which emits light in the red part of the spectrum. The chromosphere is home to prominences, giant arcs of gas that erupt from the sun's surface. These prominences can extend thousands of kilometers into space and are often associated with solar flares. The corona is the outermost layer of the sun's atmosphere, extending millions of kilometers into space. It is a vast, tenuous region that blends into the solar wind which streams out into the solar system. It's much hotter than the photosphere, with temperatures reaching millions of degrees Celsius. The exact reason for the corona's extreme heat is still a subject of scientific research and debate. The corona is visible during a total solar eclipse as a faint halo around the sun. This ethereal glow is one of the most spectacular sights in astronomy, offering a glimpse into the outer reaches of our star's atmosphere.